Welcome to the Astrophysics Podcast. Did you ever live in an apartment building and never really meet any of your neighbors? It feels kind of weird not knowing your own neighborhood, so let's take a stroll around our neighborhood and get the lay of the land. Of course, most of us know our solar system, 8 planets and their moons, thousands of dwarf planets and comets, at least 1 million asteroids that we've observed so far, along with anything else I forgot, all orbiting around our sun. So what does our sun's neighborhood look like? At the moment, our nearest stellar neighbor is Proxima Centauri, which is a star a little over 4 light years away. Our sun, of course, lives in a galaxy called the Milky Way, and from that perspective, we kind of live out in the sticks. The densest, most exciting, fast-paced part of the Milky Way is in the central bulge, the bright, sunny-side-up egg yolk part of the galaxy. We're living out in one of the spiral arms out in the crusty egg whites. By the way, as a side note, the Milky Way is the only nearby galaxy we don't actually have a photograph of because you'd need to be outside the galaxy to take the pictures. So a lot of what I'm telling you is just inferred from our astronomical data of nearby stars. Okay, so what if we go bigger? What does the Milky Way's neighborhood look like? Well, we have a couple dwarf galaxies that orbit the Milky Way called the Magellanic Clouds, which are visible to the naked eye in the southern hemisphere. Our nearest big galaxy is Andromeda, and we live in a small collection of galaxies called the Local Group. The Milky Way and Andromeda are the 2 biggest galaxies in the Local Group, each of us weighing about 1.5 trillion times the mass of the Sun. If we want to go any bigger, we should probably talk to our guest today, Dr. Kyoung-Soo Lee, Professor of Physics and Astronomy at Purdue University. Dr. Lee studies all things relating to the very largest structures in the universe, galaxy clusters. We will talk with her about what our galactic neighborhood looks like and what we can learn about it using the latest astronomical data. I'm Paul Duffel, and this is the Astrophysics Podcast.
I'm a little nervous because I've never done this before.
Well, yeah, I hadn't done this before when I started recording, so I have no idea how
did you even come up with this idea to do a podcast? I mean, that's pretty different from most of us come up with, which is not very original.
I don't know. I started listening to podcasts, and then I don't know. So I listened to podcasts. I didn't listen to science podcasts, really. I just listened to a lot of different ones. Yeah. And I hear what they were doing, and I was the guests they're getting on here, I can get on really good guests because they're because I know these people. So I thought I don't know.
It's a good idea. Yeah. No, it's awesome. It's awesome.
So let's get started. Welcome to the Astrophysics Podcast. I am Paul Duffel, and my guest today is Dr. Kyoung-Soo Lee, Professor of Physics and Astronomy at Purdue University. Dr. Lee, thank you for joining me on my little podcast.
It's my pleasure. Hi, Paul.
Hi, Sue. So I like to get started by just talking about you personally and how you grew up to be a scientist. So let me start by asking, where did you grow up?
So I was born and raised in South Korea, specifically the capital city, Seoul, where I studied until high school there. I've never been to Korea. So what was it like? So Seoul is a big city. That would be an understatement. Yes.
I don't know. Okay.
I think I'm pretty sure it's bigger than New York City.
Bigger than New York City. I didn't know that. Wow. Okay. So what was it like growing up there?
It was nice. I have mostly fond memories. I think the education system there is quite different than here. So, most people have trouble, difficulties getting through junior high and high school for different reasons than here.
Okay.
They made us study very, very, very hard.
I see.
But other than that, I
so it's just
like
very intense. They just have extremely high standards.
Yeah. So there's no extracurricular activities or other no emphasis on anything else.
Other than just...
Yeah, we were basically just like studying all the time, which was hard.
And that's basically everybody there?
Yeah.
Everybody that age is just...
That's right, until you graduate from high school, and then you're off the hook, which is also different.
Wow. So what about, I mean, surely there's like people who are not like as, who are not as academic bound as you were, that like are, you know, just like, I mean, it's not, sure not everybody, like there's some people goofing off, maybe?
Yeah, I'm sure. Yeah.
Okay, but you didn't talk to those people.
Yeah, I wasn't in that group, I suppose.
I see. But it was just very, you didn't have the same sort of thing here where, you know, you go to school, but then you'll also go to basketball practice, or you'll go to...
No, I mean, you know, so we had a handball team. So my school was actually pretty famous for, you know, being good at handball.
Oh, okay.
Which is one of those sports that I've never seen played in the United States.
Oh,
I'm
really?
sure.
I've seen it in New York City.
Really?
Yeah.
Okay. I mean, it's actually quite fun to watch.
Yes.
But I mean, but those were just as, you know, serious handball players. They, you know, I think they probably got some athletic scholarship to college, that sort of a thing. But there's no. So what I mean by, yeah. So what I meant what I said. So there is no extracurricular activities that, you know, people don't just play sports.
I see.
As part of their daily routine.
I see.
It's quite different there. I'll tell you another thing that is different there. That so here, people, especially girls, but generally anyone who is good at science and math and that sort of things, are, you know, they are called nerds. And, you know, some oftentimes, you know, in movies and otherwise, I've sort of noticed that people sort of refer to them in, you know, somewhat, you know, funny way. They're like nerdy and you know, geeks, and you know, that doesn't exist in Korea. So like
that concept.
Concept of nerds
doesn't exist
it's
in
like
Korea. That's
That's
what you're supposed to be.
Yeah, so the people actually like, you know, like you for being good at math, because then, you know, these people can help you. So there's, it's a little different.
Okay.
And then I think, you know, to some extent, you know, in US, some girls may get pressure not actually be good at math,
right?
Because then, you know, you're not supposed to be good at math.
That's not, that's not very ladylike. So then you're saying in Korea, at least in your experience, that wasn't like women were just as encouraged to go into math and science.
Yeah, absolutely.
Wow. I didn't realize that. Do you have a memory of the first time you were interested in science, or was it just all pervasive? Like, yeah,
I cannot really pinpoint this one moment when, you know, my eyes opened up for that sort of thing. But I mean, you know, I think it started early on, and maybe back when I was in junior high, I was already reading about black holes and, I don't know, the universe, and somehow like it just caught my attention, and then I think it sort of built up from there until this moment. So I don't know. I mean, maybe some people have some dramatic moment that is very, you know, memorable.
I don't think we usually have a dramatic, like, sudden moment, but anyway, some people can think of, like, I don't know, some childhood memory or something, but it doesn't. Usually I agree, isn't usually like a sudden moment that you're like, now I'm gonna do this, you know. So then were your parents big influences on getting into science, or?
Neither of my parents studied science, so I think maybe it was just the stuff that I was reading growing up, I was known to be reading a lot of books. I was like a bookworm. So
I see.
I was reading about all sorts of things, but I think, you know, at one point I started reading more and more into those subjects.
I see. So what did your parents do, if you don't mind me asking?
My mother was a school teacher.
Okay.
Elementary school. My father worked. He was in the real estate business. I mean, not selling and buying, but sort of evaluating the the prices of assets and that sort of thing.
So, but I guess they weren't like, I guess as you said, like it wasn't it wasn't a culture that discouraged girls from getting into science. So there wasn't any kind. They were happy to see you being a bookworm, and
I think so. Yeah.
Okay. So then, do you think? I know it's kind of so you didn't have a specific memory you can latch on to, but is there any? I mean, do you think generally the experiences you had as you were younger led you into astrophysics, or?
Yeah, so like I said, I was reading a lot of books about the universe, black holes, and all the mysterious stuff that I knew nothing about, and a lot of the explanations that I found in, like, I think I was reading some Scientific American at some point, the translated version, and I mean, a lot of things didn't make sense to me, and then I sort of figured that because I don't know enough physics, and so that's what sort of prompted me to major in physics as an undergrad. Yeah, and we also, growing up, I think in South Korea, we didn't have a lot of good programs teaching astronomy and astrophysics. There were a couple, but I knew that in U.S. there's a lot of really good programs. So that's so I think early on I knew that I wanted to get a PhD in astrophysics and learn more about. So
you knew like there was stuff that you were interested in that was relating to that you didn't quite, like, you'd read about but you didn't quite understand, and you thought, like, if I just knew a little bit more of this physics stuff, and then I would and so then so you had this, so then your plan was to come to America and do astrophysics. So like how?
Yeah, very naively, that had been my plan all along.
Well, apparently it wasn't naive. So. But so then you're okay. So how did that progress? Did you do college in Seoul, or?
I went to college in another city, still in South Korea, and then I came here in year 2000 to enroll in the graduate program.
Okay. And where did you go to grad school?
Johns Hopkins University. That's in Baltimore, Maryland.
Yeah. Okay. Okay, cool. And so then, how did you find that? How did you find that transition when you came to America?
A total culture shock.
Yeah.
To begin with, it was very different, and I didn't know what I had expected because I grew up watching a lot of American Hollywood movies.
Sure. Yeah.
I mean, obviously, real life is not like Hollywood movies.
But then you get surprised by the little things that are true. Right.
That's right.
But anyway, so is there anything particular you remember, like coming to America that was like?
You mean about people or the environment?
I don't know. Just I guess culturally, like when you showed up here, like is there anything that you said that took you by surprise?
One thing that I was surprised about is that you would have to drive to somewhere to do just about anything.
That's funny. Yeah, and that's Baltimore too.
Yeah,
right? So
but I mean that is true for most places in the United States, unless you're like at the heart of New York City or something. You would still have to, it would still require a car to go, from place A to B. And
that's true. It's even true for the most part, even in Seattle, where I grew up, and but and LA for sure. But it is very weird that's because most places globally, if you're in a big city, you don't need a car, and but for some reason we decided to go a different direction, so that was surprising to you. Anything else interesting? It's okay. You don't have to.
I don't know, like what people eat kind of surprised me.
Oh yeah.
The amount of soda that people, my classmates are chugging down at every meal.
Just pure sugar that we consume constantly. Yeah, we like sugar, and our high fructose corn syrup. Then, okay, let me ask you this then. When do you feel like you first learned how to be a scientist? That's
a good question. Probably later than most people.
Okay.
I don't know, like as a graduate student, I mean, of course, I learned a lot from my advisor and from, my classmates and other, astronomers. I should actually mention here that, so I went to Johns Hopkins University, as I said, and so right across the street from Johns Hopkins University Physics and Astronomy Department is a Space Telescope Science Institute, which is the institute that controls Hubble and now James Webb.
Yes.
So it was really an exciting environment in the sense that it's not just the one advisor, my advisor that I worked with, but there, I was exposed to, probably close to 100 astronomers, generally working in one or the other building. So that was a really inspirational environment that I got to talk to a lot of people, lots of talks, presentations given any given week. So that was nice. So I learned a lot, but I don't know. To be a real scientist, to feel like a real scientist, I mean, you kind of have to come up with your own ideas, think about, something that nobody has suggested before, all like on your own. And I think that didn't happen until I was a postdoc, maybe.
Yeah. So, is like there a problem that you remember first working on that you were like, that you feel like was your own?
Yeah. So I did this PhD dissertation as a graduate student, and I think I would like to think that we answered a lot of questions that the answers were not necessarily known at the time. But then I think you probably know what I mean, Paul. That
yes.
You do a project, and then you figure out some things, but then it sort of opens up a whole new set of questions that need answering now, but you still don't know.
And it is kind of funny. It's good and bad. Like if you're very optimistic, it's like, oh great, like all these great things to work on. But then if you're kind of like, okay, there's stuff that I have to do. Come on.
That's right. So I like the part where like you're sort of like figuring out a new project to answer the questions that you want answers to. But then actually getting to do and actually doing the deed. It's quite different. But I like the part of like thinking about what can I do to actually answer, figure this one out, right?
So I guess the question I originally asked was when you learned how to be a scientist, and you were saying, like you felt really more like you did this as a postdoc. So what would be the thing, like what is the thing that you felt like was like your first, like you were saying, like where it was, where you came up with the idea yourself, and it felt like your project where you had enough understanding of what was interesting in the community that you could figure out like your own project. Do you have an example? Can you think of that? Or since you said it happened as a postdoc, so
yeah. So I probably shouldn't mention any specifics here, but so the results, the result. I mean, I don't want to go all technical on you.
Oh, okay. Well, that's okay. but like just the basic idea, I guess.
Yeah. So we were sort of trying to understand how the galaxies trace dark matter structures,
right?
And so we made this measurement for the first time, and that was all very exciting and nice. But then it sort of pointed to the possibility that galaxies don't just continuously form stars to grow bigger, but it kind of like turns on and off like a switch every hundreds of millions of years, and they kind of have to go off, otherwise it wouldn't actually explain what we were measuring.
I see. So you're saying like I just to get a sense of what you mean by this, like so when the stars form in galaxies, it's not just like a continuous process whenever there's gas around the stars are forming, but it needs certain conditions to turn on, but not only that, but it like suddenly can turn on and off.
Yeah, something has to like make it turn off after so it turns on, the gas goes, and the galaxy galaxy will start turning the gas into stars, and by doing so, you're just getting brighter and brighter because much of the galaxies. Galaxies are bright because it has lots of stars, right? So the smaller galaxy with the fewer stars will be fainter. So that's sort of like we understand how the galaxies grow. So turning gas into stars is the easy part. But then you kind of have to understand why galaxy would stop doing that at one point and goes back to dormant. And
do we understand that at all now?
It's probably something called feedback. So I was studying galaxies that will evolve into something like our own Milky Way. So it's not particularly big or massive in the average. I mean, it's sort of like an average galaxy, isn't it? Our Milky Way. So so these galaxies, and we're looking. So we're looking back in time when galaxies like those, our Milky Way galaxies, would have been much smaller, so they don't have a lot of mass to and therefore it doesn't have a lot of gravity. So sometimes you have a stars form, supernovae go off, and so on, and then can expel gas sufficiently far away from the galaxy that is basically star formation shuts off temporarily, and some of the gas will eventually fall back and then maybe start the next period of growth. But so it looked like based on our results and the analysis, it looked like something like that has to happen to most small galaxies in order to explain what we were measuring.
I see. Okay, and so this is where you felt like you were coming up with the project on your own, and and understanding like that this process of star formation in galaxies can't be described in a really simple way.
That's right.
It has all these complicated things, and you were kind of showing that was inevitable based on what you had observed. That's pretty cool. Yeah,
it was kind of nice to. So we did actually. I did come up with an idea to test this theory, and I did publish another paper. But I mean, that was the very first project that I sort of can honestly say that I came up with on all on my own, which was kind of liberating and terrifying at the same time. What if I'm wrong?
Yeah, I mean that does have that sort of feeling to it, and I think overall it's mostly empowering and it makes you feel like I can actually do this. I don't need just have my advisor tell me what to work on. I can come up with my own good projects.
That's right. Did that happen to you? Something like that?
I think.
Well, you never listened to your advisor ever.
I argued with him a lot, but I think by like the last year in grad school, I was probably like, because I did a lot of. He would come up with 1 million projects for me, and I had to figure out which. Like I couldn't do all of them. I would be wasting all of my time. So I had to like figure out which ones was gonna not be a waste of my time.
Oh yeah.
So it kind of ended up being that I ended up developing that sense.
Selective hearing.
That's right. Yeah, exactly. I had to bring something up like, no, that won't work. that wouldn't. I'll spend a year doing that, and it won't get us anywhere. So yeah, I think that's how I developed that, and then I think by my last year of grad school, I was probably coming into his office and be like, what if we did this? Yeah, that type of thing. Yeah. So
sounds similar.
All right. So now you're an astrophysicist. So what are some things you like the most about your job?
Good question. Do I have to pick one?
You don't have to, no.
I mean, I can't honestly say that I like everything that I have to do as part of my job. Let me be honest about that. But a couple of things that I do like. I like teaching undergraduate level astronomy class. As you know, we're in a big engineering school, so there are lots of engineers who have like no background whatsoever in astronomy or physics.
That's right.
But they are very interested, and it kind of reminded me of where how I started started with. And so I like teaching undergraduate astronomy classes that, many students would come to me at one point and said, something that, we talked about blew their minds. And, it's very gratifying to hear something like that.
That is one of the things I love about astrophysics is even, there's lots of people here, even in the physics department, that work on condensed matter physics or other things. But astrophysics is the one thing that seemed like I feel like universally people think is cool and interesting and would seems like a fun class to take. And so it's very, I agree. It's really neat to be, especially you get a bunch of engineers who most of their courses are, just very career focused and okay, you need to learn this in order to be able to figure out how to build this. But then to take a class where it's just, let's just think about what the universe is doing.
Right. And then it's also that a lot of missions, solar system exploration, or a lot of now the results coming out of James Webb and before Hubble, gets a lot of press coverage, right? So as I am teaching this course, and then I actually have to actively pay attention to what's coming out in the news and press releases, because the things are it's that dynamic, right? Things are constantly changing.
Yes.
And one time I was teaching about the solar system, and then they announced that I kind of forget the name of the mission. This spacecraft went all the way to an asteroid named Bennu, took the sample, and then brought it back. Sent it back. I don't remember
the name of the mission, but
so that was last year ago, I think. And that was just mind blowing, because I've been showing the picture of that asteroid Bennu for years, and it just I just didn't know, because it's not my field, right? I just could not believe that they actually sent the spacecraft. Landed on it, took the sample, and sent the sample back, and
that is pretty cool to be able to just keep up with the crazy things that were going on.
Right.
Right.
And you asked me about what I like the most about this job. So the other thing, I love this element of discovery, and maybe I don't know about theorists and people who do simulations, but occasionally as an observer, which I am, you kind of find something unusual or something that is surprising. And then I think the field is moving more and more away from that, because now we're doing everything systematically. We are interested in measuring things like dark energy, and which is all very important, right? But as someone who studies galaxies, there's still a lot of weird galaxies or some weird structures that I didn't really set out to find, but then we ended up finding them. And I think that's probably what made me the happiest.
Is when you see something what is that?
Exactly.
What's happening there?
I have no clue what's going on here, but there it is, right?
As a theorist, when I see something like that, my code does something like that, I go, what's that? Usually it means there's something wrong with my code. So I stop having that feeling when something looks really weird in my results. I go, okay, what did I do wrong? But so let me ask you now, this is the one you might not want to answer. Is there anything you don't like about your job?
Once again, do I need to pick one?
It's probably best if you just pick one.
I don't know. I don't dislike most things that I have to do.
You don't have to answer it if you don't want to. I always just say, begging people for money, which is a large part of the job, right? Is writing
good
grants.
Point. Writing grants. Well, the writing grants, yes and no. Yes, I dislike the fact that we have to do it every year, multiple times a year, to find the money for our students so that, we do our jobs. But at the same time, like writing grants also, make me sort of think about, what I want to do next.
Oh, I see. It helps you sort of focus what the future.
Yeah. But except that these days, writing grants, you kind of have to have done half of the job already before you actually write.
That's right.
But so I like some part of grant writing. Yeah, but you're right. It's a pretty low on the
I didn't mean, you feel free to pick your own answer, but I just felt like you were looking through the list of things and be like, which one should I not say?
In case anybody at Purdue actually listens to this podcast.
No, they don't.
Well, the other thing that I didn't quite love is teaching this huge class, which I know for a fact that you haven't done yet.
I've gotten away with not doing that yet.
Yeah, you're lucky that way. So when you have like 300 students packed in the classroom and nobody asks any question, they all have poker face. I cannot even tell whether or not they're getting this. And it almost it's not important to know like who is getting it and who is not, because there's so many of them. Some will get it, some others will have no clue, and it's really difficult to gauge the room and see if I'm doing a good job. I need to do it differently.
That's got to be demoralizing. It's sort of like giving a lecture over Zoom.
That's right. That's right.
You're like everyone's got their screens turned off, and you're just. You're like, I hope you're enjoying this.
Or maybe you're there, maybe not.
Maybe not. Whatever. Okay, I can see that being pretty demoralizing. So I don't look forward to that, but I'm sure it is inevitably on the horizon for me at some point.
Your time will come, like it or not.
All right. One more question about you and how you got into science. So what would you say was the most challenging part of getting to where you are in academia?
That's a good one. I think I didn't love this idea or lack of clear idea where I was going to end up like 2 years down the road. Once I graduated with a PhD, and then I had to do a couple postdocs, and I think that period was rather uncertain, and I didn't like. I'm an adventurous person, but I don't like that kind of uncertainty, and I didn't need that kind of uncertainty in my life at the moment. I had just gotten married, and my husband's also an academic, and which makes it a little bit difficult.
Right, you both want to get a job at the same place.
Which is very challenging.
Right,
to do.
right.
And
it's only like every so often each department, like every some number of years, they'll have one position open in the department. So.
I mean, it's let me just say that it's sufficiently difficult for one person to find a job in a place that they would be happy with. So doing that twice in the same year or any other year is pretty difficult. So I think of myself very lucky that way. But
and me too. So we're going to move into just talking about how about your work in science and that sort of thing. So let me start with this question: when you meet a new grad student or a fellow scientist and they ask you what you work on, what do you tell them?
Oh, that's a good one. I mean, it depends on if it's a grad student or a fellow scientist. The answer would be different.
But somebody like you're just meeting and they don't know your work or whatever.
But astronomer still, or wanting to be one.
Somebody who's in astronomy. Or wanting to do it.
Yeah. So I would say galaxy formation, large scale structure. Distant universe, that sort of thing. So whenever I start my first class of a given semester, I would say I study galaxies far and far away.
Far and far away.
taken from Star Wars.
Oh, right. And it's still galaxies far, far away.
Yeah.
I should have gotten that reference. But yes. So basically the biggest structures that we can see in the universe.
That's right.
And so you say, and it's easy to sort of think, because galaxies are one thing, but galaxy clusters are this whole even bigger phenomenon that we can see. So what is a galaxy cluster?
We all know that we're in a galaxy called Milky Way. It's just one galaxy. It has about, 100 billion stars and thereabout in just in our galaxy. So imagine a structure that is big enough to host hundreds, even thousands of galaxies that are like our own, or perhaps even bigger than our own galaxy. So that's a galaxy cluster.
So hundreds or thousands of galaxies will kind of clump into a sort of cluster.
Hundreds to thousands.
Hundreds to thousands of galaxies will clump into
that's right.
And form these sort of large clusters. Okay, so why do we care about galaxy clusters?
Oh, that's a good question. So we know for a fact that the galaxies, the way the galaxies are born and grow, and the kind of, what kind of galaxy, what kind of properties that a given galaxy has. We know that it actually depends a lot on its environment, meaning, we are in West Lafayette, Indiana, we don't have big cities nearby, for 60 miles or so, right? The closest city is about 60 miles, right? Just to take a parallel here is, so somebody could be living in the downtown Manhattan, New York City, and you could have people who are living somewhere in near Death Valley, very isolated. There's no houses for miles and miles and miles, and so galaxies are also like that. We see galaxies that live in galaxy clusters. We see galaxies, for example, our own galaxy, Milky Way, our own galaxy, is not in any galaxy cluster, but it's in a place called the local group, within which we're kind of the one of the big guys. We and Andromeda, right? And then there we see galaxies that are in the void, kind of like somewhere in the very, very isolated.
So
and
I'm
these
embarrassed
galaxies,
to say now, I don't know enough about my own neighborhood. So the local group is not. So it's the local group is this little kind of isolated group of galaxies.
Small group.
How many are there in the local group about?
Oh, good question. I think hundreds, I think. And then most of them are dwarf galaxies, much bigger. It's much smaller than Milky Way.
Okay.
Andromeda is the biggest.
But so then local group doesn't count as a galaxy cluster.
No, it's not. Too small.
It's too small. Yeah. So we're not in one of the big... We're out in the sticks.
We're kind of in the suburb.
In the suburb.
Yeah, so we are falling into a galaxy cluster called the Virgo cluster. So we are the local group, and that is Milky Way, Andromeda, and all the dwarf galaxies are actually falling towards Virgo cluster because of gravity, because the Virgo cluster is much bigger.
Okay, so that's our nearest big city.
That's right. So that's Indianapolis.
That's Indianapolis. We're in Milky Way is West Lafayette.
That's right. That's right.
And Andromeda is like Bloomington or something. But I don't know. Anyway, but so
so we want to study galaxy clusters because we want to, to sort of have a proper context of why Milky Way is the way that it is, as opposed to understand why Milky Way is very different from galaxies that we see in the galaxy clusters. It is also very different from the kind of galaxies that live very isolated, not in any galaxy group like the local group. So we need to sort of understand, how galaxies are influenced by their environment that we call the large-scale structure environment.
Right. So gravity makes these structures on all different types of scales. You got stars, and stars can be in clusters, and then they can be in, and then there's galaxies, which are a whole bunch of stars, and then galaxies will also form clusters. Like you can imagine there's this whole hierarchy of scales that can exist due to gravity. But then galaxy clusters, that's as big as it gets.
So far, yes.
So
galaxy clusters are the largest, most massive structures that have sort of relaxed under its own gravity.
Okay.
We also have something called supercluster. So that's a structure that is made of multiple galaxy clusters, if you can even imagine that. But because the universe has a finite age, it's only about 13.7 billion years old since the very beginning. So these superclusters have not had enough time to actually relax under its own gravity. So it's still forming. So if you give the universe enough time, and the even larger scale, more massive things will form. But galaxy clusters, you can think of it as...
You can argue that galaxy clusters haven't exactly formed yet, sort of. But
galaxy clusters have fully formed.
They're formed, but they just haven't relaxed. So it's like they're not...
Superclusters are not.
Sorry, good. I just... Okay, good.
Yeah.
Good. All right, I just used the wrong words. Let me start... We'll try to keep all of that so everyone knows what an idiot I am. But so superclusters, you can argue, haven't really formed yet, but you can see that they're going to. You can see that that things are kind of bound, and they're going to form into a supercluster, and so we can identify them as a supercluster. And then, but galaxy clusters are the big structures that are really formed and relaxed, like you said.
Correct.
Okay.
Correct.
Good. Now I have to decide whether I can edit that out. But so I need to make sure my editing doesn't. It's not a big deal if I sound like an idiot. I just need to make sure that
you did not sound like an idiot.
Okay, good.
Don't worry.
Okay, good. So then, all right. So what were we talking about with these clusters? So they're the environments that galaxies form in, and so I guess something like the Milky Way will form in a different environment than something that's in the Virgo cluster.
That's right.
And that will affect how the galaxy grows and.
Yeah. So it may sound unlikely, but it turns out that galaxies actually can have major collision with another galaxy. So that's what we call galaxy mergers. And we think that most galaxies that we see in the universe has at least experienced the one major merger. Smaller, more like a fender bender type things also happen a lot more often. But major merger is like a pretty catastrophic kind of an event when it comes to the galaxies.
And so that's when two galaxies of this around the same mass sort of
that's right,
merge.
similar masses, they sort of merge head on, and then they form different galaxies. Bigger, one single bigger galaxy, right?
Yes.
So you can imagine, if you're in the downtown Manhattan, and then you're trying to walk in a straight line, it's going to be a lot more difficult to do so in Manhattan compared to somewhere in the desert.
Right.
So
yes, you're not going to encounter as many.
Right. So there's a lot of galaxy interactions that take place in clusters.
Yes.
And we also, when those mergers take place, and then we actually do expect to see some pretty extreme astrophysical phenomena that happen, unusual things that you don't necessarily see in other environments. So it also gives us some opportunities to study this extreme physics and these understand these phenomena.
So are most galaxies in clusters? Or so that's the question.
No. Most galaxies are in group environment.
Okay, like ours.
That's right.
Okay. So most of us are in. Okay. So clusters are very big, but they're not where most of the galaxies are.
Right.
Okay. I'm just curious about that because I was thinking about it, what are the odds that we're in a current? What are the odds that we're just in a group? But the answer is pretty decent, I guess.
Yeah. So I think we are pretty. We live in a pretty average. In a place next to a pretty average star, in a pretty average looking galaxy, and a pretty average environment.
Yeah.
So
okay. So let me ask, what does your research look like? You're an observer. So what sort of stuff do you do, like on day to day, or I guess what is?
Yeah. So I work with data. I also actively take data. So that means that. So we actually travel to or connect virtually to a telescope, and we actually take data from telescope. So in addition to the grant writing that I love so much, that means that I also have to write a lot of observing proposals to sell my idea. You know, that we want to do this because it's going to be cool. I mean, you know, I'm not allowed to actually say that, but
you're not allowed to say, well, it's going to be cool. That's why we should study it. You have to use a little bit better language than that in a grant proposal, or in a observing proposal. So a lot of taking data, and then also trying to get time on telescopes.
That's right. And once we have taken the data, and then it's all digitized, right? So we have to analyze the data, and then process the astronomical data to make sure that it's science-ready quality, which is also fun. No, it's actually fun.
Oh, okay.
But sometimes it can be tedious, and then you have weird problems that we don't quite understand, and so on. But I do like that part of the process.
Well, you're a bookworm, so
right, yeah.
you like getting
I like
your hands dirty with the data.
I like to figure things out. I think that's probably my favorite activity.
So then, so what, I had a question I thought of, because I remembered just, I don't know, like when James Webb was coming online, my mom was asking me, well, are they still going to use, like, what are they going to do with Hubble now that they have James Webb? Like, they don't need that anymore, do they? So what do you say to that?
So they operate at different wavelengths.
Yeah.
So Hubble mostly, I mean, the kind of things that you can see with your eyes, so that they're firmly within what we call the visible wavelengths. But they're light that is have a different wavelength on either end of the visible wavelength spectrum. So Hubble mostly operates still alive, so operates in the ultraviolet and visible and the near infrared. James Webb starts at near infrared and to the mid infrared, so it's quite complementary to each other. So I don't think Hubble should go because James Webb is here.
But also, like, even if they, like, of course they don't overlap, but even if they were exactly the same wavelength, you would still apply for time on Hubble, right?
Sure. Yeah. Definitely.
It's still like an incredible telescope.
Yeah.
That even, I was just realizing, like, just how long ago it launched, but it still gives like some of the best data. It's not as good as JWST anymore, but it still gives it's still one of the top observing observatories.
Yeah, I think it launched in '93, if I remember correctly.
I don't know the year,
so
but
like
it's around there.
30 years.
But it's still one of the top observatories in the world.
That's right, because we have this pesky little thing called the atmosphere.
That's right.
And then I do a lot of ground-based observing, so we have to observe through the atmosphere, and of course, atmosphere is wonderful. That's why we are all
right. It comes in handy for us humans, but
to stay alive, for example. But the visible wavelength, the kind that you can see with your own eyes, the atmosphere is pretty transparent, so you can still see when the weather is nice. So ground-based telescopes can still compete with Hubble sometimes in some ways. For example, Hubble is a small telescope, 2.2 meter. We have on ground-based in the ground, we have telescopes that are 10 meter, so much bigger, and they're working on building telescopes that are like 30 meter, 40 meter, right? So there are some things that you can do perhaps better from the ground, but the Earth atmosphere is pretty opaque to infrared, and that not only opaque, but atmosphere itself actually emits a lot of light in the infrared. So that's kind of complicate things if you want want to study, objects in mid-infrared, for example.
Right.
So that's where James Webb actually comes in handy, because it's outside of the atmosphere.
Right.
Actually, very outside of the atmosphere.
Yeah. So definitely, just the fact. I mean, just when you have a space telescope, just by itself, just that you're above the atmosphere, already gets a huge bonus.
That's right.
And so, So anyway, good. Yes. Let's not let Hubble throw Hubble under the bus just because we have our shiny new telescope.
I agree.
What would you say? What do you think of as, like, I don't know, either your most impactful contribution, or what you think is the most sort of exciting result that you've been working on?
Oh, okay. So I think I'm pretty confident. I think I can pretty confidently say that this project that I've been working on in the last couple of years are maybe I'm the most proud of.
Okay.
So we are doing this big survey program, and I said earlier about galaxy clusters being the largest structure that has fully formed. And when I said fully formed, and then that is today, right? So the astronomical observing is like a time machine, in the sense that because the light travels at finite speed, so if you are looking at things that are far away, and then in fact you're actually looking at something that happened in the past, oftentimes billions of years in the past, right? So I study these systems that will end up looking like Virgo clusters, or maybe even Comma cluster, which is a really big Comma cluster has at least 1,000 galaxies members that we know of. So something like that, but far back in the past, well before they actually fully formed as a galaxy cluster. So we call them protoclusters, because proto meaning like before it became clusters. Yes. And so I said earlier that because of all these galaxy mergers and interactions between different galaxies, you sort of, especially when they merge together, you expect to see pretty spectacular things that you don't normally see in the nearby universe. So what apparently these galaxy clusters that we see today, all the galaxies are pretty dead. And by that, what I mean is that they're no longer forming stars. So they're just like, they have each galaxy is fully formed and have fully formed some 10 plus billion years ago. So all the stars are pretty old.
So galaxy clusters today, if you look, just to clarify what you're saying, so if you look at galaxy clusters like Virgo that are today, the galaxies you see in them are like, they're mostly not forming stars.
That's right.
Now they've basically done, they're old systems that have basically done forming stars. Is that because, or I don't know, do we know why that is?
So that's what we're trying to figure out.
Okay.
So we know that it happened.
Okay.
And we know this in multiple different ways by studying galaxies in local galaxy clusters. So we know that they have not formed new stars in the last 10, plus billion years.
Okay. So is the idea that because they're in these dense environments, they just age faster or something, like, or?
So I think we understand how stars form. We have a pretty good understanding of that. So by studying these cluster galaxies nearby, we can basically figure out when they must have stopped forming. Okay. They're also much bigger, so the generally accepted idea is that these galaxies that live in the present day cluster environment, they have formed earlier and perhaps more violently, and then they stopped forming stars also very early.
I see.
So they peaked early.
Okay, I see. lived a fast life in a big city.
Yeah, and then been growing old passively in the last much of the
I see.
the time much of the history of this our universe, right? So so we're trying to sort of understand. So we're sort of looking back in the time when these galaxies were sort of like coming up, or maybe all these weird things are happening that led to their death.
I want to clarify, because I talked about something similar with Erica about this concept of looking back in time, but we might as well mention it again. Like when you see something, when you look at the sun, you're not seeing it exactly as it is now. You're seeing it what it looked like 8 minutes ago, because it takes 8 minutes for light to get from the sun to you. And the further away you look at something, you're looking at it as it was, however long it took the light to get to you ago. And so when you look at these really, really distant things, these the most distant objects you can, these really distant, what do you call protoclusters, you're able to look at, because you're looking at them back in time, potentially how long ago, like?
It's about, when universe is about 1.5 to 3 billion years old.
So 1.5 to 3 billion years old, and the universe today is about 13 to 14 billion years old.
That's right.
And so that's pretty early on. When I guess around when these things are started. Actually, when do they start to form? It's like
galaxies. Galaxies. I mean, James Webb is finding galaxies that are at when universe is like 500 million years old or so. So we do know the galaxy formation started earlier.
Okay. But then these protoclusters are there at like what you said, like 2 or 3 billion years. That when the universe is about 2 or 3 billion years old. Okay, and so these are the systems that you have been looking at.
Yeah.
Okay, and so sorry, I interrupted you to clarify that. So what were we saying about them?
First of all, galaxy clusters are also pretty rare in the nearby. Likewise, so these are the kind of protoclusters, are the same systems. You're just like looking back in time when they're much younger. So they're also pretty rare. So protoclusters have been studied in the last decade or a bit more than that, but mostly people will find the one system here, and then oh my god, look at this, there's all this different galaxies. But then another investigator would find another system using different methods, and find exactly the opposite result. So because there are such massive rare systems, and that we don't really know what is the best way to find them. So previously we've been mostly limited to case studies and using different types of methods, and we didn't really understand like what's the intersection, like what kind of system they were selecting if you're using this or that method.
Right. So I think this happens a lot in astrophysics when you're first discovering a handful of new objects. Like the first one you see, you're like, you imagine, okay, what if every object is like this? and then you see a second one, you're like, whoa, this is totally different.
Yeah, it's very wishful thinking.
It takes a while before you sort of get a sense of like an overarching sense of what these systems look like generally.
Yeah, as a scientist, we sort of have this tendency to generalize and perhaps overgeneralize things.
That's right.
And I mean, I'm sure this is the case in every level, but one of the running jokes in observation astronomers is that if you do a study of a survey of 5 galaxies, and then you may find something similar, like 3 of them may be kind of similar in some ways depending how you look at it, but the other 2 will be totally different. And it doesn't really fit neatly into any category that you make up based on previous studies. So so galaxy clusters, protoclusters, maybe like that, especially if you're selecting them in different ways. Some are just serendipitously, just by happenstance, they just got by mistake discovered. Then there are some that are found in different ways, and so what we're trying to do is this in a more consistent, systematic way, and also try to make a big enough sample so that we don't have to have like 5 protoclusters,
Right.
and then 2 of them are totally weird.
Right.
So this survey is ongoing, and once it's finished, we should have like hundreds. It's about 500-600 protoclusters that we are expected to find. So that's kind of exciting.
Yeah. And that's very, very cool, because it's like it's basic. It's our sort of first look at kind of getting a general understanding of how these clusters, how they form, like being able to directly look at that process rather than just kind of speculating.
Right.
So that's very cool. And so. Is there anything you can already say that's exciting about it, or you don't have to?
Yeah, there's a bunch of different things that are coming out based on our early data, but one of the things that I didn't really expect, I actually, to be honest with you, I don't know what I expected. Maybe I had a zero expectation, but so we are finding this objects. It's really weird. We call them blobs.
Okay.
So
blobs.
Blobs are gas that is strongly emitting some emission line called Lyman alpha. And so these are big. So typical galaxy at the redshift that we're looking at is about 2-3 couple of kiloparsec. It doesn't matter if that doesn't, you've never heard of kiloparsec. It's a distance unit. So these blobs, these gas clouds, can be as big as 100 kiloparsec, which means that you could have tens of galaxies, typical galaxies inside.
Okay.
It's
but what you see is this blob of bright or whatever. What do you call it?
It's a hydrogen gas.
Yeah. You can see. Yes. You see this blob of hydrogen gas.
Yeah.
It's big enough. It's big enough. It could have like tens of galaxies in it.
Lined up, not inside. Lined up in a single file.
Lined up single file.
That's right, because it's 100 kiloparsec across. So you could actually have probably big enough to have thousands of galaxies in them.
Okay.
But we don't, not that we see thousands, but
I see. So that definitely, when you see something like that, that's going to pique your interest.
Yeah, that's right. And then so don't get me wrong, so we knew that these blobs existed before. What we didn't know was that they tend to abound around the protoclusters. So I think they are related to, I said earlier about all these head-on collisions between galaxies, and their interactions might actually give rise to interesting phenomena we don't necessarily see elsewhere. And I think this might be one of those phenomena that somehow all the galaxies in protoclusters and this environment, they're sort of falling under gravity, right? So they're all falling to the center of gravity, which is where all the galaxies are.
So when you imagine them all being in this sort of line, it's like they're all sort of, it's like sort of it's like a chain of them falling inward towards some larger structure, or gas is everywhere,
right? But I think when something like that major merger happens, and somehow some of the energy gets out and sort of light up all the gas around them, and then that's how that's what blobs are most of the times. And I guess we're gonna have to go and validate this theory one way or another. What our data is just giving you the circumstantial evidence that we do see a lot of these near dense protoclusters where there are a bunch of galaxies are living, but it doesn't really tell you why they light up.
So it's funny, counterintuitively, whenever you hear an astrophysics term and it's something like with like a name like blobs, which sounds like a really poorly thought out name, usually those are the really exciting things, because we haven't figured out a better name yet, because we don't understand it.
That's right.
And so that's very cool. So I guess it's basically, the more we look at those, the more we can try to build our theories as to how these sorts of, what is actually going on there.
Yeah, there's a lot of things that we don't really quite understand out there. So, and I think that is really the best part of doing this, being an astronomer, that you get to sort of answer things that people didn't even know existed.
Right. Okay, well that hopefully leads to our next question, which is, in your opinion, why should we care about astrophysics?
Why not? I don't know. I mean, everybody has their own interests, but I mean, I'd like to think that, astronomy is really one of the, those studies that really seeks answers to where we came from. So I think it maybe not direct way, but sort of answers where we came from, sort of give us better understanding of why we're here. I don't want to get all philosophical on you, Paul, but
that's the nature of this question.
Yeah.
Ends up forcing people to be philosophical. But it is a question that's relevant to our careers because we're being paid to study astrophysics, so it's good if we have some answer for that. But it's definitely I think there's no question that it's interesting, and that I think everybody would like to know more about where we came from. So so then let me ask you, what is you know what's next on the horizon, or what are the next big things you're interested in solving, or
yeah, so I mean, like I said, we're still in the middle of this survey program. So I'd like to make sure that we get good results and the survey reaches its full potential. So there's still some, projects and questions that I'd like to find some answers to before I look to different things.
Okay.
But yeah, so I mean, we are looking at different kind of astrophysical phenomena. I mean, I mentioned blob as one example, but there are other weird things that we're finding in our surveys. And so, yeah, so I think a lot of as the survey is sort of ramping down, which was sort of like halfway past, so sort of like slightly past the midpoint, maybe closer to the finish line than the starting point.
Yes.
So now we are writing a lot of observing proposals to look more deeply into some of these objects, so that we can say something more concrete about what is going on. And
okay, so in other words, once you've done the survey, you can follow up on specific objects.
That's right.
And look more closely at them.
Right. And I'm also excited about a lesser-known space telescope called Roman. So James Webb is stealing all the media coverage right now, but Roman is, if you remember what I said earlier, so James Webb is all the way out to the mid-infrared, and it can do multiple things. Roman is infrared telescope. It's mostly dedicated to imaging. So James Webb is also like very tiny. So if you can think of sort of the full moon area before our full moon, right? So it looks pretty big, but it's quite small in as a fraction of the entire sky. James Webb can look at tiny little bit of the full moon. So you wouldn't be, if I were to draw a, rectangle corresponding to that in the side, on the surface of the full moon, you wouldn't be able to see it. It's that
tiny little bit.
That's right.
The James Webb's field of view.
Right. So you can study everything so well.
Right. In that one little bit.
Right. But it's not a big survey instrument that you can go and look at huge area. Roman is different. So Roman is going to look at huge area of the sky at a time. So that's actually going to be very powerful for the kind of things that I am doing, because I'm looking at the largest cosmic structures, which are much bigger than, at least as big as a single structure is as big as the full moon. So
that's very.
It's a bit of a problem if you want to go and pick a tiny region to target with James Webb, which we'll still do, but you have to very carefully pick a truly special region, because these things are big.
Yes, it's interesting you mentioned that James Webb did get the huge fanfare, but to astronomers, like Roman is at least as famous, at least now, because it was kind of suddenly announced. And so it didn't have the same like big press buildup that James Webb had, but it definitely is going to be a big impact on all sorts of fields in astrophysics. So I think that's all. I think we've gone on for a while. I kept wanting to ask you more questions. So let me wrap it up and say thank you so much, Dr. Lee, for joining us. I had a lot of fun talking science with you, and I hope you'll join us again sometime.
Yeah, sure. Thank you, Paul.
Very cool. If you hadn't heard about the Roman Space Telescope before, I can give you a few of the basics. It's named after the astronomer Nancy Grace Roman, designed specifically for infrared surveys. Its major scientific goals are to search for exoplanets using a technique called microlensing, and to study the growth and assembly of structure in the universe, to understand how the universe has expanded over time, which will help us to constrain what is causing it to expand faster and faster. But there will also be many other valuable uses for the Roman telescope, and we look forward to seeing it launch, hopefully in 2026. So thank you again, Dr. Lee, for helping us to learn about our neighborhood, and thank you to our listeners. We will see you next time. The Astrophysics Podcast is supported in part by the National Science Foundation under grant number AAG 2206299. The music you hear on the Astrophysics Podcast was written and recorded by Britton Ashford. They are instrumental versions of songs from her album Trotter. All songs are used with permission from the artist and producer. Check out her music if you enjoyed it. This podcast is produced in beautiful Lafayette, Indiana by me, Paul Duffel, professor of physics and astronomy at Purdue University.